Hello there, welcome to Ethio-Hahu tutorial. I'm Ethio and today we are going to see about simple pendulum. Consider a particle of mass m tied at the end of a string of length L as shown below. The string makes an angle theta with the vertical and there are two forces acting on this particle of mass m. One is gravitational force which acts vertically downward, and the other is tension force, tension in the string. This gravitational force is resolved into two components. One is tangential component, which is mg sine theta, and the other is perpendicular component, mg cos theta. Since this angle is theta, this angle is also theta. Therefore, mg sine theta is the tangential component tangent to this circle, and mg cos theta is perpendicular to this circle at this point. And here, the restoring force is equal to minus mg times sine theta, because this mg sine theta tends to move the block to its equilibrium position. This is the equilibrium position, and it moves the system to its equilibrium position. But for a small angle theta, sine theta is almost equal to theta, and cos theta is equal to 1. For very small angle theta, this angle theta, sine theta is approximately equal to theta, and cos theta is equal to 1. Therefore, the restoring force is equal to minus mg times sine theta is theta. Again, from the relationship between linear quantities and angular quantities, this is x, this arc length is x, the length of the string is L, and this is the angle subtended by this arc length, and theta is equal to x divided by L, where theta is this angle, x is this arc length, and L is the radius of this sector. And substituting this into this equation, the restoring force is equal to minus mg times, in place of theta, x divided by L. This is equal to minus of mg divided by L times x, where mg divided by L is a constant, minus kx, and this is known as Hooke's law. From the period of simple harmonic motion, we know that period is equal to 2 pi the square root of m over k, and substitute for k mg divided by L. This is equal to 2 pi the square root of m over k is mg divided by L. mg divided by L. M cancels by m. This is equal to the square root of L over g. Therefore, the period of simple pendulum is simply 2 pi. Here we have 2 pi. The square root of L over g, where L is the length of the string and g is acceleration due to gravity. And this is the period of simple pendulum, which is independent of mass of the system. Rather, it depends upon the length of the string and acceleration due to gravity. Having seen this, let's do example. The first example says a pendulum bob is made from a sphere filled with water. What would happen to the frequency of vibration of this pendulum if the sphere had a hole in it that allowed the water to leak out slowly? Since the period of simple pendulum is given by period is equal to 2 pi the square root of L over g, and from this, the frequency is 1 over 2 pi the square root of g over L. The period of this simple pendulum is independent of mass, rather it depends upon the length of the string and acceleration due to gravity. So it's true for its frequency. Therefore, if we have a simple pendulum having a hole that allows water to leak out, then the period of simple pendulum cannot be altered, since the period or frequency of simple pendulum is independent of mass, the frequency of vibration. The frequency of vibration does not change. That means the period of simple pendulum given by 2 pi, the square root of L over G, remains constant, independent of mass, and the frequency is also remains constant. The frequency is equal to 1 over 2 pi the square root of G over L is also constant. Even though the water leaks out of the hole, since the period of simple pendulum and the frequency of the simple pendulum does not depend upon the mass, the period as well as the frequency remains constant or unchanged. The second exercise, a simple pendulum has a length of 50 centimeters and makes 80 complete oscillations in 2 minutes. Find the period of the pendulum and B, the value of G at the location of the pendulum. To do this, let's have given the length of the pendulum is 50 centimeters, which is equal to 0.5 meter, and makes 80 complete oscillations. Number of oscillations is equal to 80 in a time delta t is equal to 2 minutes, which is equal to 120 seconds. A, what is the period of the pendulum? The period of pendulum. And B, the value of G, acceleration due to gravity. A, to find the period, first let's find the frequency. Frequency is simply number of oscillations made divided by time needed, and the period is time needed to complete this number of oscillations. Number of oscillations. This is equal to the time required is 2 minutes or 120 seconds divided by number of oscillations 80. 1 0 goes with 1 0, by 4 2, by 4 3. 3 divided by 2 is 1.5 seconds. Therefore, the period of this simple pendulum is 3 over 2 seconds or 1.5 seconds. B, to find acceleration due to gravity G, since in A we have found that period is equal to 1.5 seconds, and from period of simple pendulum period is equal to 2 pi the square root of L over G, and squaring both sides period square is equal to 4 pi square L divided by G. And from this, G is equal to 4 pi square L divided by period square. G is equal to 4 times 3.14 square times L is 0.5 meter divided by period square is 1.5 square. Since all are in SI units, just we can leave the units, and this implies G is equal to 8.76 meter per second square. This is acceleration due to gravity at the location of the pendulum. The next exercise, a simple pendulum has mass 1.2 kilogram and length 0.7 meter. What is the period of the pendulum near the surface of the earth? And B, if the same mass is attached to a spring, what spring constant will result in the period of motion found in part A? Given mass of the pendulum 1.2 kilogram and the length of the pendulum is equal to 0.7 meter. What is the period of the pendulum near the surface of the earth? A. Assuming that G is equal to 9.8 meter per second square, period is equal to 2 pi the square root of L over G, and period is equal to 2 times pi is 3.14 times the square root of L is 0.7 meter divided by G is 9.8 meter per second square. This is equal to 1.68 second. The second question, if the same mass is attached to a spring and oscillates back and forth as a simple harmonic motion, what spring constant will result the same period as that of the simple pendulum? That means if this mass is attached to a spring of force constant K and has the same period as that of the simple pendulum, what would be the force constant of this spring? The period of simple harmonic motion is equal to 2 pi the square root of m over k. This implies the period of this simple pendulum, the simple harmonic motion, is the same as the period of this simple pendulum. That is, period of simple harmonic motion is equal to 1.68. Having this, 1.68 is equal to 2 pi the square root of m over k. Squaring both sides, 1.68 square is equal to 4 pi square m divided by k, and k is equal to 4 pi square m divided by 1.68 square. This is equal to 4 times 3.14 square times m is 1.2 kilogram divided by 1.68 the whole square, and k is equal to 4 times 3.14 the whole square times 1.2 divided by 1.68 the whole square, and this is equal to 16.77 Newton per meter, or approximately equal to 17 Newton per meter. The force constant of the spring has to be 17 Newton per meter for this mass to have the same period as that of the simple pendulum. And this is all about today, and see you next time.